Welcome to this explainer. Okay, today we are diving into a microchip architecture that is so bleeding edge, it honestly sounds like pure science fiction. We're talking about the Steam Quad Engine chip. This isn't just your standard run-of-the-mill incremental tech update. No, this is a complete fundamental reimagining of materials and geometry that could literally rewrite the rules of modern computing.
So, let's set the baseline here. The target performance for this wild concept? 103.5 quadrillion calculations per second. Yeah, you heard that right. That is an unfathomable number with 15 zeros. You know, in the engineering world, we're totally used to throwing around terms like gigaflops or teraflops, but jumping into the quadrillions, that pushes computational throughput into an entirely different stratosphere. But honestly, wrapping your head around a number with 15 zeros is pretty tough.
To really grasp that scale, let's ground it in a human comparison. Imagine one person doing just one calculation a second. It would take them 3.28 billion years to match just a single second of this chip's target output. 3.28 billion years. Even if we recruited the entire planet, like if every single one of the 8 billion humans on Earth did one calculation a second, it would still take our entire global population 150 days of non-stop math to equal what this thing aims to process in a single heartbeat. Absolutely mind-boggling.
Here's our roadmap for this explainer. First, we'll look at the math behind a quadrillion calculations. Second, we'll break down the anatomy of a carbon chip. Third, we'll look at the 10,000 simulation crucible. And finally, we'll explore how this could actually change the world.
All right, jumping right into Section 1, a quadrillion calculations, setting the target.
So, to hit that massive mathematical target, this design completely tosses out the traditional single-brain architecture. You know how standard chips often bottleneck because they're desperately trying to juggle way too many tasks at once? Well, instead, this concept relies on extreme parallelism. It uses 4 distinct engines, and each one is stacked with 10 specialized layers dedicated to specific jobs, like routing, logic, and heat spreading. By breaking the workload apart so drastically, the architecture achieves a highly optimized separation of roles. The theoretical pathway here is simple. More engines and more layers directly equal more throughput.
Okay, moving on to Section 2, Anatomy of a Carbon Chip, Building the Impossible. Let's pop the hood and see how this thing is actually built, because it is wild. This chip completely avoids standard metals, no copper, no aluminum. That is a massive, massive departure from standard semiconductor manufacturing. Instead, it relies on a shungite and graphene stack. Shungite provides this really stable carbon base, while the graphene offers extreme electrical conductivity. And they pair this with boron nitride for electrical insulation, plus a material called MOS2, which is molybdenum disulfide, normally used as a solid lubricant. Here, it acts as a semiconductor and spreads heat. Now, actually building high-density interconnects without any metal, that's a huge engineering hurdle. But theoretically, this stack offers the ultimate mechanical stability.
Right at the very center of this architecture sits a genuinely brilliant feature, a diamond dome. It acts as both a rapid thermal chimney and a critical data hub. Because diamond-like carbon has incredibly high thermal conductivity, it pulls heat out super fast, while simultaneously acting as a shared coordination point. This setup is what allows those 4 independent engines we just talked about to behave seamlessly, like one unified system.
Now, surrounding that dome is what the designer literally calls a whale brain network. Each of the 4 engines contains 12 subregions, creating 48 specialized processing lobes that all communicate through that central hub. But okay, it gets even wilder. Tucked right under the dome is a hollow, kind of Twinkie-shaped core that actually uses physical vibration and resonance to assist with timing and signal gating. Think about that for a second. The chip is literally using structural physics and physical waves to drive computer logic.
To prevent hotspots from, completely melting this intricate network, the architecture utilizes a 6-branch snowflake geometry. You can think of it like a highly symmetric rapid exit highway for both heat and data. Instead of your standard grid, these branches offer much shorter paths outward from the core. This makes sure that thermal energy and information are evenly distributed across the surface, which vastly improves the chip's theoretical lifespan and performance.
Which brings us to Section 3, the 10,000 simulation crucible, stress testing reality.
Look, a concept is really just a fancy drawing until it actually survives the physics simulator, right? So the developers threw 10,000 rigorous stress tests at this blueprint, checking everything from shrinkage variance to laser power fluctuations. The results?
a staggering 98.8% total pass rate right out of the gate. For heat dissipation alone, across 3,200 test cases, it scored 98.7%. Interface defects sat at 97.8%, but in the world of microchip manufacturing, 98.8% simply isn't good enough. Those 120 specific simulation failures meant the design still needed refinement. To hit that flawless 100% pass rate, the engineers went back in and implemented 3 highly specific physical adjustments. First, they added 6 100-micrometer thermal vias, basically microscopic heat escape tunnels, at the edges of the snowflake branches to stop edge heat trapping. Second, they bumped up the drying time by 5 seconds to prevent uneven material shrinkage. And third, they set a hard minimum limit on the manufacturing laser power to 450 milliwatts, and even added an auto shut-off monitor just to make sure the diamond layers formed correctly. With those fixes applied, the simulated thermal performance is almost unbelievable. Despite churning out over 100 quadrillion calculations, the steamship runs at a maximum hotspot temperature of just 42 degrees Celsius. That is 50% cooler than your standard Intel i9 CPU, which regularly hits 85 degrees. The simulation basically confirms that the combination of the diamond dome, the snowflake geometry, and those new thermal vias completely eliminates dangerous hotspot buildup. It's really incredible.
And what's just as impressive is the proposed manufacturing speed. I mean, traditional silicon wafers can take weeks, sometimes even months, to process in a foundry. But this entire manufacturing cycle, driven by a precision purple laser that selectively transforms regions of carbon into a diamond-like phase, it takes just 3.83 minutes per unit. Actually, scratch that. Think about it. It's less than 4 minutes to produce a chip that can handle quadrillions of calculations. It is a wildly efficient theoretical production line.
All right, moving to our final section. Section 4, Changing the World, the Final Vision.
So here's the big question. What actually happens if this mathematically verified simulation becomes a tangible reality? A chip with this much processing power, packed into something the size of an SD card, unlocks a world where medicine, energy, and environmental cleanup operate without computational limits. Imagine energy grids with such tight control loops that power outages become a thing of the past. Picture drug discovery where protein screening happens in days, not decades. We are talking about running highly personalized AI tutors locally, right on your device, without needing massive cloud server farms. It represents a total paradigm shift to a world of absolute compute abundance.
But, we do have to remain grounded here. Aspirational outcomes are one thing, but overcoming the actual physical limits of non-metal manufacturing is a massive, massive hurdle. A successful 10,000-run simulation proves the math works. It proves the thermodynamics balance out perfectly in a digital vacuum. But physically building real-world, high-density device layers and contacts without standard metals, that is a monumental task. It's something the semiconductor industry has yet to fully solve.
Which leaves us with a profound question about the bleeding edge of engineering. We have this blueprint that absolutely conquers the simulation, scoring a 100% pass rate after those brilliant structural adjustments. But can we actually build it? Will the physical prototype withstand the chaotic, messy realities of real-world manufacturing? The steam quad engine concept shows us a dazzling roadmap of what is computationally possible. The next step is waiting for someone bold enough to try and print it. Thanks for joining me on this explainer, and I'll catch you on the next deep dive.